Determining unloaded quality factor Q from two-part measurements. We have seen that the quality factor of loaded resonator is given by 1 over quality loaded equals 1 over quality external plus 1 over quality node or unloaded quality factor. The unloaded quality factor of the resonator is a property of the resonator, but the external quality factor is a property of the resonator as well as a property of the added load to the resonator. This means that the external quality factor is changing by changing the load. So, to design a specific problem, it is required to determine the unloaded quality factor, and from the unloaded quality factor and determining the external quality factor for the specific problem, we can obtain the loaded quality factor of the resonator. So it will be required to determine at the beginning the unloaded quality factor of the resonator. Actually, to determine the quality factor of a resonator, it means that we are going to connect the resonator with a probe. And this probe has an internal characteristic impedance. This is equivalent to connecting the terminal of the resonator by a value of the impedance equals this characteristic impedance. Assuming that we are going to measure the quality factor of a series resonant circuit by using two-port measurements. This means that we are going to connect the input port of the resonator to a probe with a characteristic impedance Z0 and connecting the output port of the series resonator with another probe with characteristic impedance Z0. This is equivalent to connecting the two terminals of the series resonator with characteristic impedance or with impedance equals Z0. This means that we have a Z0 in this port and a Z0 in this port. Or, in other words, we are going to connect this series resonant circuit with a load impedance equal to Z0, because effectively this Z0 would be series with this Z0, and they are connected directly to the series resonant circuit. So in this case, the unloaded quality factor, it would be Q naught equals omega naught L over R, where L is a corresponding inductance inside the series resonant circuit and R is the internal resistance inside the series resonant circuit. On the other hand, the external quality factor QE in this case would be omega naught L over the real impedance connected to the series resonant circuit, which is 2Z0 in our case. So this is the external quality factor in the case of two-port measurement. So the total quality factor or the loaded quality factor in this case, 1 over Q loaded would be 1 over Q external plus 1 over Q naught. We can simplify the problem by taking 1 over Q naught as a common factor. So in this case, it would be 1 over Q naught multiplied by 1 plus Q naught over QE, or unloaded quality factor over external quality factor. We know that Q naught over QE is defined as the coupling factor of the resonator, which is G. So in this case, the loaded quality factor 1 over Q loaded would equal 1 over Q naught multiplied by 1 plus G, where G is a coupling coefficient. Or in other words, we can say that Q naught would equal Q loaded multiplied by 1 plus G. The unloaded quality factor, which is required to be determined, equals 1 plus G, 1 plus the coupling coefficient, multiplied by the loaded quality factor. Effectively, what we can measure is the loaded quality factor. The output of the measurement in this case is the loaded quality factor in this case. So, we can determine the loaded quality factor from the measurement, and if we could determine the coupling coefficient G, we can determine the unloaded quality factor. And once we can determine the unloaded quality factor, we can obtain the loaded quality factor for any other load. Alright? In the present case, the coupling coefficient G equals 2Z naught over R, where 2Z naught is the attached load, the impedance of the attached load, over R. R is the internal impedance of the series RLC resonant circuit. Okay? Alright. The question now is how to determine the value of G. As I said, G equals 2Z naught over R. By measuring the transmission coefficient for this two-port network from port 1 to port 2, we can find out that S21 equals 2Z naught over 2Z naught plus the impedance of the resonant circuit Z of omega. How this relation has been obtained? Effectively, we can say that for port 1, the input impedance seen by port 1 is Z of omega, which is the impedance of the resonant circuit, plus Z naught, because Z naught here in series with Z of omega. So Z of omega plus Z naught is the input impedance here. The reflection coefficient is Z input minus Z naught over Z input plus Z naught. So in this case, the reflection coefficient would be Z of omega plus Z naught minus Z naught over Z of omega plus Z naught plus Z naught. This is the reflection coefficient. The transmission coefficient S21 is given by 1 plus S11. So the transmission coefficient in this case would be 1 plus the reflection coefficient. So it is 1 plus Z of omega over 2Z naught plus Z of omega. By taking a common factor 2Z naught plus Z of omega, we can obtain 1 minus gamma as 2Z naught over 2Z naught plus Z of omega. So this is the transmission coefficient here. At the center frequency or at the resonant frequency, the value of Z of omega, it would be R, because at the resonance, the input impedance of the series RLC circuit is directly R. So at the resonant circuit or at the resonant frequency, Z of omega, it would be directly R. Now, the transmission coefficient at the center frequency is 2Z naught over 2Z naught plus R. And we know that the coupling coefficient is 2Z naught over R. So, by dividing both the numerator and the denominator by R, we can rearrange this transmission coefficient as 2Z naught over R plus 2Z naught over R plus 1, or in other words, G plus 1 plus G. G over 1 plus G. Okay? S21 is already measured. So we can obtain the coupling coefficient in terms of the measured S21 as G. It would be S21 at omega naught over 1 minus S21 over of omega naught. This by solving this equation. Here S as a function of G, we can obtain G as a function of S. So this is the coupling coefficient. So at the center frequency of the resonant circuit, we are going to measure the value of S21 or the transmission coefficient, and from the value of S21 we obtain S21 over 1 minus S21 as the coupling coefficient G. Now we have already obtained the value of G. What about the loaded quality factor in this case? This is simply can obtain by F naught over the bandwidth. So by measuring S21, we take the peak as the resonant frequency, and we obtain the bandwidth of minus 3 dB with respect to this peak. We obtain the bandwidth of minus 3 dB with respect to this peak. So the value of the center frequency over the 3 dB bandwidth, the measured 3 dB bandwidth, so F naught over the bandwidth would correspond to the loaded quality factor in this case. Now we have the loaded quality factor from the measurement, and we have the coupling coefficient from S21. So we can obtain the unloaded quality factor Q naught as 1 plus G, which we have already determined from S21 as the center frequency, multiplied by the quality factor, which we have already determined by the value of the resonant frequency and the value of the 3 dB bandwidth measured from this resonant circuit by the two-port network. So by using the transmission coefficient for this series resonant circuit, by using input probe and output probe with characteristic impedance Z0, we could obtain the unloaded quality factor of this series resonant circuit. Q naught equals 1 plus G multiplied by the loaded quality factor Q load. Okay? Alright.